Picture the Earth from far above, turning slowly in the dark. It looks calm, blue oceans, white clouds, brown continents drifting past like a scene painted on glass. Nothing about that view tells you the planet is holding a secret deep inside its own body, one that has surfaced again and again across hundreds of millions of years. Beneath the crust, beneath the mantle, in a churning ocean of molten iron, something moves that will one day undo the very idea of north and south. Somewhere in your home tonight, or in a boat, or a hiking pack, there may be a compass. Its needle points north with a kind of quiet confidence, the way it has for every person who has ever used one. Sailors trusted it across empty seas. Explorers trusted it through blinding snow. But that needle is not obeying a fixed law of nature. It is following a magnetic field that is, in truth, always shifting, always drifting, and has flipped completely many times before. North has become south, south has become north, not once, but over and over, across the deep history of this planet. We don't know exactly when it will happen again. We don't know exactly why it happens at all. What we do know is written faintly in old volcanic rock and in the silent mud of the ocean floor, like a diary the Earth did not mean to keep. Before we go further, the planet has a new quiet wonder to share every night. If you'd like one waiting for you each evening, subscribe and let it come to you. Let your body settle now, because this is not a story that needs to move fast. Think of the planet as a slow breathing thing, not a solid rock, but a layered sphere, with a thin outer skin of crust, a thick mantle beneath it, and at the very center, a heart of iron. Part of that iron heart is liquid, swirling under pressure so immense it is difficult to imagine. That churning liquid iron is what makes the magnetic field in the first place. It is not fixed. It is not painted on like the lines on a globe. It is generated moment to moment by movement, and movement by its nature can shift. Scientists have found the evidence of these shifts frozen into rock. When lava cools, tiny mineral grains inside it lock into place, pointing toward whatever direction was north. At that exact moment, layer after layer of cooled lava, stacked up over millions of years, shows those tiny compass needles pointing different ways, sometimes north, sometimes south. The rock remembers what the surface world forgot. This is the heart of the mystery we will sit with tonight. What triggers a full reversal when the entire field flips from one pole to the other? What happens to the field in the long, uncertain stretch when it is neither fully one way nor the other, weak and wandering, as if the planet is unsure of itself? And what, if anything, that means for the living things on the surface? Breathing air, following old migratory paths, going about their quiet lives above a shifting compass they cannot see. There are ideas, there are theories, some competing, none proven completely. One idea points to the churn of the outer core itself, chaotic by nature, prone to instability the way any turbulent fluid can be. Another asks whether the deep mantle above the core plays a role, its uneven heat pulling the core's currents into different rhythms. Neither idea fully explains why reversals come at such uneven intervals, sometimes tens of thousands of years apart, sometimes millions. We know reversals have happened many times in Earth's past. We know they are not sudden or violent, more like weather changing over centuries or thousands of years than any kind of moment. We do not know exactly when the next one will begin, or if the field's current weakening, which researchers have been watching closely, is even related. For now, high above the swirling iron center of the planet, the compass still points where it always has, this morning and tonight. It feels permanent, because a human life is so brief compared to the slow turning of the Earth. But permanence on this scale is only an illusion built from timing. Somewhere beneath your feet, in a place none of us has ever seen, that iron ocean keeps moving, indifferent to the maps we've drawn, indifferent to the words north and south. Tonight, let your mind rest on that vast, patient churn. Let it hold you gently, the way the planet's own hidden magnet has been quietly holding its shape and slowly losing it for longer than any story we've ever told about it. Let's picture what a compass needle actually points toward. It does not point to a place on a map, it points along invisible lines of force, lines that loop out of the Earth, arc through the sky above us, and dive back in at the other end. We call this whole shape the magnetic field, and it wraps our planet like a soft, unseen skin. You cannot see it, you cannot touch it, but birds can sense it, and so can your compass, and so, in a much larger way, can the entire planet we live on. To understand where this field comes from, we have to travel down, way down, not just past the dirt and the roots of trees, not just past the rock we quarry and mine, but thousands of kilometers beneath our feet. The distance from the surface to the center of the Earth is about 6,370 kilometers, or roughly 4,000 miles. If you could drive that distance at highway speed without ever stopping, it would take you more than 2 days of steady driving, straight down, through solid rock the entire way, near the very center of that long drive, past the crust we stand on, and past the thick, slow-moving mantle beneath it, you would reach the core. And here is where things get strange. The core has two parts. There is an inner core, a solid ball of mostly iron, about the size of the moon, sitting at the center of our planet under crushing pressure, wrapped. Around that solid ball is the outer core, and this part is not solid at all. It is liquid. It is a moving ocean of molten iron and nickel, roughly 2,200 kilometers thick, hot enough to melt almost anything we know on the surface. This liquid metal ocean is where our story really begins. Iron conducts electricity very well, and when a conductor like iron moves, especially while the Earth spins beneath it, it can generate electric currents. Those currents, in turn, create magnetic fields. This churning, spinning liquid iron acts something like the coil of wire inside an old electric generator, except the coil is a swirling ocean of white-hot metal, larger than the entire planet Mars. Scientists call this natural process the geodynamo, a name that simply means the Earth is dynamo, or generator. The temperature down there is extraordinary. The outer core sits at somewhere between 4,000 and 6,000 degrees Celsius, a heat close to the surface of the sun. And yet, because of the pressure at that depth, the inner core stays solid even at temperatures that would vaporize iron near the surface. This is one of the quiet strangenesses of our planet. Solid metal, hotter than most fires we can imagine, held together not by cold, but by the sheer weight of the Earth pressing down on it from every side. How old is this whole system? The Earth itself formed about 4.5 billion years ago, and the best evidence we have suggests the magnetic field has existed for most of that time, perhaps 3.5 billion years or more, though the exact age remains an open question among researchers. Some rocks in Western Australia hold magnetic signatures that old, faint traces of a field already shielding the planet when life was still nothing more than simple cells in ancient seas. That shield matters more than it might seem. The magnetic field reaches far out into space, deflecting streams of charged particles that flow from the sun, a moving current we call the solar wind. Without this invisible shell, that wind would slowly strip away parts of our atmosphere, the same way it likely did on Mars, a planet that lost its own magnetic field long ago, and with it much of the air that once surrounded it. So we are left with a strange and quiet picture beneath our feet. An ocean of molten iron turns slowly in the dark, generating a field none of us can see, stretching far past the sky, shaping the flight of birds, the drift of whales, and the gentle swing of every compass needle ever made. It has been doing this for longer than almost anything else on Earth has existed. And yet, as steady as it feels, that liquid ocean of iron is never still. It shifts, it swirls, it changes its patterns in ways we are only beginning to understand. That restlessness is where our real mystery starts to take shape. If the field comes from something moving and alive in that sense, always churning, never quite settled, then perhaps it should not surprise us that the field itself is not fixed either. Perhaps a needle that has always pointed one way could, given enough time, learn to point another way entirely. We will follow that thread slowly, the way the iron itself moves, one patient turn at a time. Let's picture the true North Pole, the one your compass points toward. It is not fixed to a single spot of ice. It drifts slowly year after year, tracing a soft path across the top of the world. A century ago, it sat quietly in the Canadian Arctic, moving only a few miles each year. Then, sometime near the end of the last century, it began to pick up speed. Today it moves faster, drifting towards Siberia at a pace that surprised the people who track it closely. This wandering is not new. It has likely been happening for as long as Earth has had a magnetic field, which is to say, for billions of years. The pole we mark on our maps is really just the surface expression of something far larger and far deeper. It is where invisible lines of magnetic force happen to point straight down into the ground, move the machinery underneath, even slightly, and the point on the surface shifts too. That machinery sits nearly 2,000 miles beneath our feet, in the outer core, a shell of molten iron and nickel wrapped around a solid inner core. This liquid metal is never still. Heat, rising from the deep interior, stirs it into slow rolling currents, the way a pot of syrup might shift and swirl if warmed unevenly from below. Those currents carry electric charge, and moving charge creates magnetism. This is the process scientists call the geodynamo, a name for a natural engine that has run, with only occasional pauses, since Earth was young. Nobody watched this engine switch on. No one could have. It came together sometime in Earth's first billion years, as the planet cooled from a molten ball into layers, a thin crust, a thick mantle, and a metal core sorted by gravity into heavier iron at the center. Some researchers believe the field may have started even earlier than once thought, based on faint magnetic signals locked into some of the oldest rocks ever found, stones over 4 billion years old. Other researchers remain cautious about those very old signals, since rock can be reheated and remagnetized long after it first formed, muddying the record. The exact birthday of Earth's magnetic field is still an open question. What we do know is that once the core began to churn, it needed to keep churning to keep the field alive. A dynamo like this does not run on its own momentum. It needs a constant source of energy, something to keep stirring the metal. That energy comes partly from heat still leaking out of the inner core as it slowly grows, and partly from the settling of lighter elements that drift upward through the liquid outer core over time. Both processes stir the pot, so to speak, and both are still active today, which is part of why the field has lasted so long instead of fading out. Because the stirring is uneven, the pole never sits perfectly still. Think of it less like a fixed pin stuck into the Arctic, and more like the tip of a slow, invisible flame, leaning this way and that as the currents beneath it shift. Over a human lifetime, that lean is small. Over centuries, it becomes a visible wander across the map. Over hundreds of thousands of years, that same restlessness in the core has, at times, grown so extreme that the entire field flipped, with north and south trading places entirely. This is the part that keeps geophysicists up at night, in the gentle, curious way that a good mystery keeps anyone up. The same churning that gives us a wandering pole today gave ancient Earth its reversals long ago. Some researchers wonder if today's faster drift is a small, ordinary ripple in a system that has always moved. Others wonder if it is an early sign that the deep currents are shifting into a different, more dramatic pattern. No one can say for certain which it is, because we have only been measuring the pole carefully for a small slice of the planet's long life. What began then was not a fixed compass needle bolted to the planet, but a living system born from heat and metal and time, always in motion, never quite finished. The pole we call North today is simply where that ancient process happens to point right now. It has pointed elsewhere before. It will likely point elsewhere again. How it got here and where it drifts next remains a story still being written in slow motion, deep beneath the ice and rock, in a place no human eye will ever see directly. Let's go down, past the crust, past the mantle, to the very center of the Earth. Here, nearly 4,000 miles below your pillow, lies a heart made mostly of iron. This is the core, and it comes in two parts. There is a solid inner core, packed so tightly by pressure that the iron cannot melt, even though it burns hotter than the surface of the sun. Around it swirls the outer core, a thick ocean of liquid iron and nickel, restless and always moving. Think about where that iron came from. It did not start here. Every atom of iron in Earth's core was forged inside a dying star. Billions of years before our planet ever formed, stars spend their lives fusing lighter elements into heavier ones, building carbon, then oxygen, then silicon, working slowly toward iron. When a massive star reaches the end of its life, it can no longer hold itself together. It collapses, then explodes, scattering iron and other heavy elements across space in a bright, brief burst of light. Those scattered atoms drifted for ages, mixing with gas and dust, until gravity pulled them together into a spinning cloud. Slowly, that cloud flattened into a disk, and inside that disk, our solar system began to take shape. Earth formed from that same drifting material, gathering rock, metal, and ice into a single growing sphere. In its early years, the young planet was hot enough to melt, and something remarkable happened. The heaviest elements, mostly iron and nickel, sank toward the center, pulled down by their own weight. Lighter materials, like silicon and oxygen, rose toward the surface and cooled into the rock we now call the mantle and the crust. This sorting process, sometimes called differentiation, is one reason the deep Earth is so rich in iron today. The core is, in a very real sense, old starlight settled into place at the center of our world. The outer core is not pure iron alone. Scientists believe it holds nickel too, along with smaller amounts of lighter elements, perhaps sulfur, oxygen, or silicon mixed in. The exact recipe remains an open question, since no one can travel down to sample it directly. Researchers study it instead through the whisper of earthquake waves, which bend and slow as they pass through different materials deep underground. From those small changes in speed, scientists build a picture of what lies below, though the exact proportions are still debated. It is worth pausing here to notice how far these iron atoms have traveled. They began inside a star, perhaps one that lived and died long before our sun ever ignited. They floated through the cold dark for millions of years. They gathered into a small rocky planet, then sank slowly downward through molten rock, settling at last into the center of the Earth. And here they remain, churning quietly, generating the very magnetic field that shields us from the sun's harshest particles. The compass on a hiking trail, the iron in your own blood, both trace back to the same stellar origin. Water tells a similar story of distant arrival. Some researchers think much of Earth's water came from icy comets and water-rich asteroids that struck the young planet during its early chaotic years. Others argue that water may have been present in the rocky material that formed Earth from the very beginning, locked inside minerals and released later as the planet warmed. Both ideas remain under study, and the true answer may involve some mixture of the two. Either way, the ocean outside your window and the iron deep inside the planet share a common thread. Both arrived from somewhere else, carried across space long before Earth existed as we know it. This deep connection matters for the mystery we are following tonight. The iron heart at Earth's center is not simply sitting still. It moves, it churns, and that movement generates the magnetic field that wraps around our entire planet. Without that iron, forged so far away and so long ago, there might be no magnetic shield at all, and no story of poles that wander, weaken, and sometimes reverse. The material itself is ancient, but its behavior remains only partly understood. Scientists can describe what the core is likely made of, yet they still cannot say with certainty exactly how its motion decides, again and again, when north will become south. For now we simply picture it, a ball of iron and nickel, born in a star's final moment, resting at the middle of our world, quietly turning. Above it, oceans that may have arrived on the backs of comets. Around it, a field invisible to our eyes, protecting everything living on the surface above. The pieces fit together, but the full mechanism stays hidden, patient and unsolved. Picture a pot of soup left on a low flame for a very long time. Near the bottom, close to the heat, the soup warms and rises. Near the top, it cools and sinks back down. This slow circle of rising and sinking has a name. Scientists call it convection, the gentle turning of a fluid as heat moves through it. Deep inside the Earth, something like this happens too. But the fluid is not soup, it is liquid iron, and the pot is bigger than any ocean. The outer core sits far beneath our feet, a shell of molten metal wrapped around a solid inner core. It is under enormous pressure, squeezed by the full weight of the planet above it. Heat rises from the inner core, which is slowly freezing and releasing warmth as it does. That heat pushes the liquid iron upward in slow, twisting loops, while cooler iron sinks back down to take its place. This restless motion never really stops. It has likely been running in some form for billions of years. As the iron moves, it does something more than simply flow. Iron is a metal that carries electric charge easily, and the Earth is spinning the whole time this movement happens. That spin bends the rising and sinking currents into long, twisting spirals, a bit like water, curling as it drains, but far slower and far larger. Moving, charged metal creates electric currents, and electric currents create magnetic fields. This is the heart of what scientists call the geodynamo. The idea that Earth's magnetic field is generated by this constant churning of liquid iron deep below. It is worth sitting with how strange this is. Nothing about the magnetic field is fixed or solid. It is not built into the planet, like a bar magnet sealed inside a rock. It is made fresh, moment by moment, by fluid in motion. The field we see at the surface, the one that guides a compass needle or a traveling bird, is really just the outer skin of a much larger, much wilder process happening thousands of kilometers down. This is part of why the field can behave in ways that feel almost restless. The currents in the outer core are not neat or orderly. They shift, they twist, they sometimes fight against each other in patterns that are difficult to trace. Some columns of rising iron may strengthen the field in one direction. Nearby currents may work against them. The overall field we measure at the surface is something like an average of all this deep, chaotic motion, smoothed out, but never fully still. One idea, supported by decades of study and computer modeling, is that this very instability is what allows reversals to happen at all. A field generated by simple, steady motion might stay locked in one direction forever. But a field generated by turbulent, shifting currents has room to wobble, weaken, and occasionally flip. In this view, reversals are not strange failures of the system. They may be a natural, if rare, outcome of how the geodynamo works in the first place. Not every researcher frames it quite this way. Some models suggest that reversals depend heavily on conditions at the boundary between the core and the mantle, that thick, slow-moving layer of rock above it. Slight differences in heat flow across that boundary might nudge the core's currents into new patterns, tipping the system toward a flip. Other models point instead to internal core dynamics alone, without much need for outside influence. The honest answer is that no single model has been proven correct. Different simulations produce different reversal patterns, and matching them cleanly to Earth's real history remains difficult. What almost everyone agrees on is the time scale involved. This is not a fast process. The currents in the outer core move at speeds of perhaps tens of kilometers a year, slow compared to almost anything we experience directly, yet fast enough to reshape a magnetic field over centuries or millennia. A reversal, when it happens, likely unfolds over hundreds to a few thousand years, not overnight, and not even within a single human lifetime. So the forces at work here are not dramatic in the way a storm or an earthquake feels dramatic. They are steady, deep, and almost unimaginably patient. Heat rises, iron churns, the planet spins. Somewhere in that combination, a magnetic field is born, sustained, and occasionally undone. We can model the outer core, we can measure its effects at the surface, but we cannot watch it directly, and much of its true behavior remains hidden, spinning quietly beneath us, moment after moment, deep in the dark. Let's think about what a magnetic field really is, in a way we can hold in our minds. You cannot see it, you cannot touch it, but you have felt its work every time a compass needle settles into place. A magnetic field is a region of space where a force reaches out, invisible, and nudges certain things toward alignment. Around a bar magnet on a kitchen table, that field is small enough to hold in your hand. Around the Earth, that same kind of force stretches out for tens of thousands of miles, farther than the eye could ever follow. Picture the planet shrunk down to the size of an orange, sitting on a table in a quiet room. The magnetic field around that orange would not stop at the edge of the table. It would fill the room, spill into the hallway, and reach toward the house next door. That is the rough scale of it. If we are honest about the comparison, Earth's real magnetic field extends about 40,000 miles out into space, on the side facing the sun, and stretches even farther into a long tail on the side facing away. It is a shape like a teardrop, squeezed on one side and drawn out long on the other, shoved into that form by a constant wind of particles streaming from the sun. Now think about where this whole vast invisible shape actually comes from. Not from the surface, not from the mountains or the oceans we know so well. It comes from deep inside, from the outer core we spoke of a moment ago, a layer of liquid iron sitting nearly 2,000 miles beneath your feet. That layer is smaller than the field it produces, by an almost strange amount. The engine room is modest. What it produces fills half of nearby space. Here is another way to feel the size of it. If you shrank the Earth down to the size of a peppercorn, the magnetic field around it, drawn to the same scale, would form a bubble roughly the size of a beach ball, a small, hard seed at the center, wrapped in something enormous and soft and invisible. That is what surrounds all of us right now, all the time, without any sensation at all. The strength of this field, though, is surprisingly modest. At the surface, Earth's magnetic field measures somewhere between 25 and 65 microteslas, depending on where you stand. A small refrigerator magnet, held right up to a compass, can overpower it in an instant. The whole planetary shield that deflects dangerous particles from space is, at ground level, weaker than the magnet holding a photograph to your refrigerator door. Size and strength, it turns out, are not the same thing at all. Age adds another layer to the wonder. Some researchers believe the field, in some form, may be over 3.5 billion years old, present not long after the Earth itself cooled enough to hold a solid crust. Others point to evidence suggesting the field may have started weaker and grown stronger over time, as the inner core slowly solidified and gave the dynamo more to work with. The exact starting point remains an open question, argued over in laboratories and in the patient study of ancient rock. What makes all of this worth sitting with in the quiet dark is the strange fact that something this large, this old, and this important is generated by something we cannot see, cannot sample directly, and cannot watch in motion. No one has ever lowered an instrument into the outer core. No one ever will, given the pressure and the heat down there, thousands of degrees, crushing weight from thousands of miles of rock pressing down. Everything we understand about the field's shape and size comes from careful, indirect listening, from satellites far above and sensitive instruments planted in quiet places on the surface. So when you think of the compass needle, think past it, out past the atmosphere, out past where the weather ends, into that long teardrop of invisible force, reaching toward the sun and away from it. Think of a small hot iron heart, no bigger than the moon, humming away in the dark center of the planet, producing a shield that wraps around the entire Earth like an unseen skin. It is a strange kind of scale to hold in the mind before sleep. Enormous, yet fragile, ancient, yet still being measured today, still surprising the people who study it. The size of the field is not really the mystery. The mystery is how something so vast can also be so ready, every so often, to lose its shape entirely and rebuild itself in a different direction. Picture a hillside in the highlands of Iceland. The rock is dark and rough, cooled long ago from rivers of lava that once glowed orange in the night. To most eyes, it looks like any other stretch of volcanic stone, pitted and grey, dusted with pale green moss. But this rock is holding on to a secret. It remembers something that happened the moment it cooled. When lava is still liquid, it is too hot to hold a magnetic memory. Tiny grains of iron-rich minerals inside the melted rock, too energetic to settle, drift and spin freely. But as the lava cools past a certain temperature, something quiet and remarkable happens. those iron grains lock into place, and they align themselves with the direction of Earth's magnetic field at that exact moment. Like a room full of tiny compass needles, all freezing mid-swing. From then on, the rock carries a fixed record of which way north pointed on the day it formed. This is the science of paleomagnetism, a word that simply means the study of old magnetism preserved in rock. Geologists can walk across a lava field, take samples the size of a fist, and read the direction those iron grains are pointing. Most of the time, the answer matches what we expect. The ancient needles point roughly toward the north, just as a compass would today. But scattered across the world, in certain layers of rock, something strange turns up. The tiny magnetic grains point the other way entirely, south. Stand for a moment and imagine walking down through layers of exposed rock, the way you might walk down a staircase carved into a cliffside in Iceland, or the Deccan Plateau in India. Each layer represents an older slice of time, stacked beneath the one above it. As researchers moved through these layers in the 20th century, testing the magnetic direction locked into each one, they began to notice something that seemed almost impossible. The direction was not always the same. It flipped, layer after layer, again and again, over millions of years. At first, this looked like it might be a mistake. Perhaps the rock had been disturbed, tilted, or somehow scrambled after it formed. But when scientists checked lava flows on opposite sides of the planet, thousands of miles apart, with no connection to each other, they found matching patterns. Layers of the same age carried the same reverse direction, whether the rock sat in Iceland, Hawaii, or the volcanic fields of France. That kind of agreement across such distance is hard to explain by accident. One idea, now widely supported by the evidence, is that these flipped layers are not errors at all. They are honest records of a real event. At some point in Earth's deep past, the entire magnetic field reversed itself, so that a compass needle at that time would have pointed firmly toward what we now call south. The rock did not lie. It simply recorded a version of Earth that pointed the opposite way. Still, questions linger over exactly how to read this story. Cooling lava can be affected by chemical changes after it hardens, and some rock types hold their magnetic memory more reliably than others. Researchers have to be careful, testing multiple samples and comparing results from different sites before trusting a signal. A single confusing rock does not prove a reversal happened. It takes patient, repeated evidence gathered slowly across many places to build confidence in what the layers are truly saying. What makes this rock record so valuable is its patience. Unlike a modern magnetometer, which only measures the field for the years it happens to be running, a lava flow can sit quietly for 100 million years, holding its answer, waiting for someone to ask. Every reversal, every wandering shift of the pole has left some trace somewhere in the crust, if only we know where to look and how to read it. And so those quiet hillsides, easy to walk past without a second glance, hold something close to a diary, not written in ink, but in iron, not read with the eyes, but with sensitive instruments that measure the faint tug of ancient magnetism. Still locked inside stone, the story is fragmented, scattered across continents, and buried under later flows, and much of it remains unread, but it hints, again and again, at a planet whose compass has not always pointed the way it does tonight. Picture a slow boat dragging a strange instrument through the deep water, far out over the middle of an ocean. The instrument does not look for fish or currents. It listens for magnetism, hidden in the rock beneath the waves. What it found decades ago changed the way people understood the whole planet. Beneath every ocean, there is a long mountain range that circles the globe, called the mid-ocean ridge. It is where the seafloor is born. Deep under the water, hot rock rises up from below, melts and pours out as lava. That lava cools and hardens, and slowly it pushes older rock away to both sides. This is the slow work of plate tectonics, the idea that the Earth's outer shell is broken into moving pieces, drifting a few centimeters each year. It sounds gentle. It is also how oceans grow wider, one thin sliver of new rock at a time. Here is where the magnetism comes in. When lava cools and turns solid, tiny grains of iron-rich minerals inside it act like tiny compass needles. As the rock hardens, those grains lock into place, pointing toward wherever magnetic north was at that exact moment. The rock remembers. It carries a frozen record of the planet's magnetic field, the same way a photograph holds a moment that no longer exists. When researchers towed their instruments across the seafloor, they expected to find a plain, steady signal. Instead, they found something almost impossible to believe at first. The magnetism rose and fell in bands, striping outward from the mid-ocean ridge like the pattern on a zebra. One band pointed north, the next pointed south, then north again, then south, over and over, mirrored perfectly on both sides of the ridge. At first, this pattern seemed strange enough to question the instruments themselves, but the stripes lined up too well to be a mistake. Rock formed at the ridge on one side matched, band for band, the rock forming at the very same time on the other side. The only explanation left standing was almost too large to hold in the mind. The Earth's magnetic field itself had been flipping again and again throughout deep time. North had become south, south had become north, and the ocean floor, quietly and patiently, had been writing it all down. This discovery did two enormous things at once. It offered strong support for the idea of moving plates, since the matching stripes proved the seafloor was truly spreading outward in two directions, and it gave scientists a timeline, a way to count the reversals stretching back millions of years, written in solid rock instead of guesswork. Still, questions remain buried beneath those stripes. The mid-ocean ridges are hard to study directly. They sit under kilometers of dark water, in places human eyes rarely see. Researchers depend on remote instruments, submarine dives, and rock samples pulled from great depths, which means every stripe pattern is a partial view, pieced together over years of careful survey. Some sections of ridge are well mapped, others remain sparse, their record thinner and harder to read. There is also the matter of interpretation. The stripes tell us that reversals happened, and roughly when they are less clear about why any single reversal began, or what was happening deep inside the Earth's core in the years before it did. The rock only records the outcome, the final direction the needle happened to freeze in. It does not explain the churning process that led there. That process, hidden far below even the deepest ocean trench, remains part of the larger puzzle. One idea suggests the process is simply the natural behavior of a fluid, chaotic system, one that flips unpredictably, the way a pot of boiling water forms and breaks its own patterns. A competing idea points to slower influences, changes at the boundary between the core and the mantle above it, perhaps shifting heat flow over long stretches of time. Neither explanation has been confirmed. Both remain open, sitting quietly beside the striped rock, like two possible endings to the same story. What is certain is this: somewhere beneath the waves, in basalt cooled and hardened over millions of years, the planet has been keeping a diary. It is written in magnetism instead of ink, in stripes instead of sentences. And even now, new stripes are forming at this very moment, far below the surface, in total darkness, recording whatever the Earth's magnetic field happens to be doing right now, for someone, someday, to read. In the early years of the last century, a French physicist named Bernard Brennes made a quiet discovery in the hills of central France. He was studying old volcanic rock, layers of dark lava that had cooled and hardened long ago. Inside that rock, tiny grains of iron had lined up like sleeping compass needles. But when Brennes measured them, they did not point north, they pointed south. At first this seemed like a strange accident, a puzzle with no clear cause. But the rock itself gave a clue. When lava cools and turns solid, the iron grains inside it freeze in place, locked forever in whatever direction the magnetic field pointed at that exact moment. Think of it like a tiny snapshot, taken by the rock itself, of the sky's invisible compass. Brennes had found a snapshot from a time when the compass pointed the opposite way. This idea sat quietly for decades, more curiosity than proof. Other scientists found similar rocks in other places, and the same reversed pattern kept showing up. Slowly, a picture began to form. The Earth's magnetic field has not always pointed the way it does now. It has flipped more than once over the planet's long history. North became south, south became north, and the rocks had been keeping the record the whole time, layer after layer, like pages in a very slow, very patient diary. What makes this a cycle rather than a single strange event is the sheer repetition written into the stone. Geologists studying rock formations from different continents began to notice the same reversed and normal patterns appearing again and again, stacked through time like sediment settling in a still pond. Each layer told the same quiet story. The field held steady for a while, then it flipped, then it held steady again in the new direction. Nothing about this rhythm follows a neat, predictable beat. Some periods of steady polarity lasted only a few thousand years, others stretched on for millions. This is one of the deep puzzles at the heart of the mystery. A cycle usually suggests something regular, something you could set a calendar by, the way seasons turn, or tides rise and fall. But the magnetic field's reversals refuse that kind of order. There is no fixed interval, no steady drumbeat waiting to be counted down. Some researchers describe it less as a cycle and more as a slow, uneven pulse quickening at times, resting at others, following rules that still are not fully understood. One idea is that the churning of the liquid outer core, that restless layer of molten iron beneath our feet, produces a magnetic field that is naturally unstable by its very nature. In this view, reversals are not caused by any single dramatic trigger. They are simply what happens, eventually, when a turbulent system runs long enough. Small disturbances build, the field weakens somewhere, strengthens somewhere else, and given enough time, the whole pattern can tip over into its mirror image. A different line of thinking looks instead at the boundary between the core and the mantle, the thick layer of slow-moving rock above it. Some scientists wonder if the shape and behavior of the deep core, its temperature, its texture, its uneven surface, might set the pace of these flips more than the mere passage of time. If this is right, reversals might depend on conditions we cannot easily see or measure, hidden thousands of kilometers beneath the surface we walk on. Neither explanation has been confirmed, neither has been ruled out. The rock record gives us the outline of the rhythm, but not the reason behind its irregular timing. What we do know is that the discovery itself changed how scientists thought about the Earth's insides. A field that seemed as permanent as the ground itself turned out to be something that moves, weakens, and occasionally turns itself inside out, the compass in your hand. If you held one tonight, is only pointing to whichever direction the field happens to favor right now. It has not always been this way, and there is no reason to believe it always will be. Somewhere in the volcanic rock of France, and in similar stones scattered across the globe, that memory still sits quietly, layer after layer, a slow archive of a planet changing its mind about which way is north. We are only just beginning to read it clearly, and much of what it says remains open to interpretation. The rhythm is there. The reason behind it is still being searched for, one magnetized grain of iron at a time. Picture a place like Iceland or the Columbia Plateau in the American Northwest, where the ground itself once ran like water long ago in slow and repeated events. Cracks opened in the earth, and lava poured out across the land in dark, glowing sheets. It moved like a thick orange river, cooling at its edges even as it kept flowing at its center. This is a common sight in Earth's deep past, and it left behind something far more useful than anyone at the time could have known. Each flow, as it cooled, became a kind of frozen photograph of the sky's invisible compass inside. That cooling lava are tiny grains of iron-rich minerals, so small you would need a microscope to see them. While the rock is still molten, these grains float freely, and they turn to line up with the magnetic field around them. The same field that swings a compass needle today. As the lava cools and hardens, the grains lock into place. They stop moving. From that moment on, they hold the direction of magnetic north, exactly as it stood on that one day, in that one place, for as long as the rock survives. Some of these rocks have survived for tens of millions of years. Geologists learned to read this record by walking across old lava fields with sensitive instruments, measuring the faint magnetism trapped in rock after rock. What they found was strange. Layer after layer, flow after flow, the direction pointed the same way for a long stretch of time. Then, in one layer, without warning, the direction pointed the opposite way. North had become south, at least as far as the compass grains could tell. This was not a single strange rock. It showed up in lava fields on different continents, formed at different times, all telling a similar story. One theory, now widely supported, is that these flipped layers are not local accidents. They are a record of the whole planet's magnetic field changing direction, over and over throughout Earth's long history. The lava did not cause the flip. It simply happened to be there, cooling at the right moment to catch the change and hold on to it. In that sense, each hardened flow is a neighbor to the event itself, sitting quietly beside a mystery it recorded but cannot explain. A competing idea, taken seriously in the early days of this research, was that something local might be at fault. Perhaps certain rocks became magnetized backward through some chemical process in the ground, unrelated to the sky above. This idea mattered because it offered a simpler explanation, one that did not require the entire planet's field to reverse. But as more sites were studied, on more continents, showing the same pattern at matching times, that explanation grew harder to support. The evidence began to point towards something larger and stranger than local chemistry. What makes this rock record valuable is not just what it shows, but where it shows up. Lava flows exist beside other kinds of natural recorders, like layers of ash, thin bands of sediment, and cooled volcanic glass, all of which sit close together in the same regions. Scientists can compare these neighboring layers, checking one against another, to see whether the same reversal shows up in more than one kind of material. When a lava flow in one country and an ash layer in another, both point the same unexpected direction, the story becomes harder to dismiss as coincidence. Even so, the picture stays incomplete. A single cooling lava flow only captures a moment, a kind of snapshot, not the slow unfolding of the change itself. It cannot show how many years passed before the field settled into its new direction, or whether it wavered back and forth before committing to the flip. For that, researchers must look elsewhere, to other neighboring records left in the mud of the ocean floor, and layered ice and sediment had built up slowly enough to catch the field in motion rather than in a single frozen instant. So the lava fields stand as one piece of a larger puzzle, offering proof that reversals happened without explaining how they unfolded, or why the field chose that particular moment to turn. They sit beside the mystery closely, like a quiet witness who saw the ending but missed the middle of the story. What caused the field to move, and how long the turning actually took, remains an open question the rock alone cannot answer. That question will lead us next into an even older and colder kind of record, one held not in stone, but in the layered floor of the sea. If we could count every flip in Earth's long story, what number would we land on? Scientists who study this have found an answer, and it is a strange one. Over the last 160 million years, the magnetic field has reversed more than 180 times. That works out to an average of about one flip every 450,000 years. But averages can hide a lot of truth, and this one hides quite a lot. The record shows something almost hard to picture. There have been long, quiet stretches when the field held steady for tens of millions of years without a single flip. Geologists call one of these the Cretaceous normal superchron, a stretch of roughly 40 million years. During the age of dinosaurs, when the compass needle would have pointed the same way the whole time, 40 million years is longer than the time since the extinction event that ended the dinosaurs themselves. During that entire span, whatever churns and shifts inside the outer core, the layer of molten iron below the mantle, never once flipped the field. Then, in other stretches of deep time, the record shows the opposite extreme. Reversals have come in tight clusters, sometimes only a few 100,000 years apart. Some scientists who study these clusters wonder if something about the flow of the outer core shifts into a more unstable mode during those periods, making flips easier to trigger. Others wonder if we are simply seeing noise, random timing with no deeper cause at all. Nobody has settled that question yet. The most recent full reversal is called the Brunès-Matuyama reversal. It happened around 780,000 years ago, and it is the last time north and south fully traded places. Since then, the field has held its current direction, with plenty of wobbles and one dramatic near miss along the way, but no full flip. That means every person who has ever lived, every civilization ever built, has existed entirely within one single magnetic direction. We have never seen a reversal happen with human eyes, only its fingerprints left behind in old rock. How fast does a reversal actually happen? Here the numbers become almost dizzying. For a long time, the assumption was that reversals unfolded slowly, over many thousands of years, since a molten ocean of iron is not something that should change quickly. But one striking piece of evidence gathered from a layer of ancient lava in Oregon suggested something far stranger. The magnetic direction, frozen into some of those cooling rock layers, seemed to shift by many degrees in a matter of weeks. That finding, published years ago, stirred real debate. Some researchers argued it captured a genuine burst of rapid field change. Others suggested local, temporary disturbances in the rock, not the true pace of a global reversal. The disagreement over that single site has never been fully resolved, and it stands as one of the strangest data points in the whole story. Most researchers today think a full reversal, seen from start to finish, takes somewhere between 1,000 and 10,000 years. That is still remarkably fast on a geological scale. Even at the slower end, 10,000 years might sound long to us, shorter than the time since the last ice age ended. Buff. Compared to the 4.5 billion years the Earth has existed, it is closer to a blink. There is another extreme worth sitting with. The strength of the field itself changes across time, not just its direction. During some ancient periods, the field appears to have been unusually strong, perhaps twice as strong as it is today. During others, including possibly right before certain reversals, it seems to have dropped to a small fraction of its usual strength. The field we live under right now sits somewhere in the middle of that range, and it has been slowly weakening for at least the past century and a half, though scientists disagree on what that particular weakening means for the future. So the honest picture is one of extremes without a clear pattern tying them together. Some ages were untouched by reversals for tens of millions of years. Some ages saw flips pile up close together. Some reversals may have unfolded in mere centuries. Others stretched across many thousands of years. No one has found the rule that decides which kind of age we are in, or which kind might be coming next. The record simply shows that the Earth's compass has always been capable of surprising us, on timescales too slow for a lifetime to notice, and occasionally, perhaps, fast enough to notice after all. If you look closely at the record of reversals, you notice something odd. They do not come on any steady beat. There is no metronome ticking beneath the surface of the Earth, no gentle clock counting down to the next flip. Some reversals are separated by only a few thousand years. Others are separated by tens of millions of years. The rhythm, if we can even call it that, is uneven in a way that still puzzles the people who study it. Picture a long shelf of ancient rock, layer after layer, each one holding a faint record of the magnetic field at the moment it cooled. Reading that shelf feels a little like reading tree rings, except these rings do not mark years, they mark magnetic moods. A geologist walking that shelf might find 10 flips packed into one narrow band of time, then nothing at all for a stretch that spans an entire ice age. The pattern seems to have no pattern, and that absence of a clear rhythm is itself a small, quiet mystery. There was a stretch of time scientists call the Cretaceous Normal Superchron, a period lasting nearly 40 million years, during which the field apparently did not reverse even once. Imagine the compass held steady through the age of long-necked dinosaurs, through the slow drift of ancient seas, through the rise of early flowering plants. Then imagine, more recently, geological moments when reversals bunched close together, almost as if the Earth were restless and could not settle. Both extremes are recorded in the same kind of rock, by the same kind of process. The question is why the pace of change is so wildly different from one era to the next. One idea points to the boundary between the outer core, that shell of liquid iron, and the solid mantle above it. Some researchers wonder if changes in how heat moves across that boundary might make the field more or less stable at different points in the planet's history. A patch of mantle rock that conducts heat unevenly could, in theory, disturb the flow of the molten iron beneath it, nudging the field toward instability. Yet, it is a hopeful idea, and a testable one in models, but it remains just that, a model. The real boundary, buried nearly 3,000 kilometers down, cannot be watched directly. Another idea looks outward rather than inward. wondering whether the pace of plate tectonics itself might play a role. As continents shift and ocean floors spread, the shapes pressing down on the core mantle boundary change too, ever so slowly. If the core's behavior depends partly on the shape of the rock above it, then a slow tectonic shuffle over tens of millions of years could quietly reshape how often the field flips. It's a graceful thought, linking the deep churn of iron to the drift of continents far above. But like the heat flow theory, it remains speculative. No one has proven a direct chain of cause and effect. What makes this rhythm even more delicate to study is the resolution of the rock record itself. Some layers hold a fine, detailed picture, cooling quickly enough to catch subtle wobbles in the field. Others are coarse and blurred, smearing together events that may have happened centuries apart into what looks like a single moment. Reading these layers is a bit like listening to an old recording with static woven through the quiet parts. The signal is there, but pulling out every soft detail takes patience, careful instruments, and a willingness to accept that some parts of the tape may simply be unrecoverable. There is something almost soothing in sitting with this unevenness rather than rushing to explain it away. The Earth does not owe us a tidy pattern. It has spent over 4 billion years being molten, restless, and slow to reveal its inner workings. A field that flips 10 times in one epoch and stays calm for 40 million years in another is not misbehaving. It may simply be following rules we have not yet fully mapped. Rules written in the pressure and heat of a place none of us will ever see with our own eyes. For now, scientists keep gathering rock samples, drilling into ocean sediment, and comparing timelines from opposite sides of the globe, hoping the pieces will someday line up into something more like an explanation. Until then, the uneven rhythm remains, one of the quieter puzzles tucked inside a much larger one. It asks us to imagine a compass needle that has, across the ages, gone still for tens of millions of years, and then, for reasons still unclear, changed its mind again and again in a much shorter span. In the early 20th century, a French physicist named Bernard Brenous made a quiet discovery in a stack of old volcanic rock. He was studying lava near Clermont-Ferrand in the middle of France when he noticed something strange. The tiny magnetic particles inside the cooled lava pointed backward instead of aligning with north, the way a compass needle should. They pointed south. At first this looked like an error, a flaw in the sample, or a fluke of one unusual rock. Brunhes wondered if the entire magnetic field of the Earth might once have pointed the opposite way. It was a quiet, careful thought, published in 1906, and for decades almost no one paid it much attention. The idea sat mostly forgotten for years. Other scientists found scattered rocks with the same backward-pointing minerals in different countries, on different continents, but the pattern was hard to piece together. It took new instruments to make sense of it, magnetometers, tools sensitive enough to measure the faint magnetic memory locked inside stone. Slowly improved through the middle of the century, researchers could now measure not just the direction of ancient magnetism, but its strength. And what they found added a new layer to Brunhes' old observation. The field did not simply flip like a switch. In many samples, it seemed to grow weak first, fading down to a fraction of its usual strength, before the direction changed at all. By the 1960s, two teams working somewhat independently, one led by Alan Cox in the United States, began building a timeline. They dated lava flows using radioactive decay, a natural clock inside certain minerals that ticks at a known rate, and matched those ages to the magnetic direction frozen in the rock. Layer by layer, flow by flow, a pattern emerged. The Earth's field had flipped many times over millions of years, not randomly scattered, but following gaps of quiet in between. And near many of those flips, the strength dropped noticeably in the rock record, sometimes to 10% of its normal power or less. This raised a question that still has no clean answer. Does the weakening cause the reversal, or does the reversal cause the weakening? One idea, favored by many working from the physics of the outer core, that churning shell of liquid iron surrounding Earth's solid center, suggests the two happen together as part of the same process. The swirling currents that generate the field can become unstable, and as they reorganize, the field's strength drops, while the poles begin to wander and eventually trade places. In this view, weakening is not a warning sign so much as a symptom, part of the same turbulent event. A competing perspective treats the weakening as something that could, in principle, happen without leading anywhere. The dynamo inside the Earth, the process by which moving liquid metal creates a magnetic field, is naturally a little unstable all the time. It could dip in strength and simply recover, the way ocean currents can slow and speed up without changing which way they flow. Researchers have found evidence of unfinished reversals in the rock record, moments when the field weakened and even started to shift before snapping back to its original direction. These are called excursions, and they complicate any simple story of weak field leads to full flip. The instruments used to study this today are far more refined than what Brunès had in his rock samples. Satellites orbiting the planet now measure the field's strength continuously, comparing modern readings against decades of prior data. Ships and aircraft carry magnetometers across oceans, mapping magnetic stripes on the seafloor with a precision no early researcher could have imagined. And still, with all this modern equipment, the fundamental question from that first lava sample in France remains only partly answered. Scientists can see that the field is weakening now, in our own time, at a measurable rate. They cannot say with certainty whether this is the beginning of something larger, or a quiet fluctuation like the ones recorded in ancient excursions. What Brunès started with a puzzled look at backward-pointing rock became, over a century, a slow global effort involving physicists, geologists, and instrument makers across many countries. Each generation added a little more precision, a little more data, without quite closing the gap in understanding. The weakening before a reversal is real, documented in rock after rock, on continent after continent. Whether it is a cause, a companion, or simply an ordinary phase of an unpredictable process is still an open question, one that keeps drawing new instruments and new attention, long after that first strange sample was pulled from French volcanic stone. Somewhere over South America and the ocean beyond it, the Earth's magnetic field grows thin. Scientists call this patch the South Atlantic Anomaly, and it stretches from Chile to Zimbabwe, a quiet dip in the invisible shield that wraps our planet. Satellites flying through this region pick up more radiation than they do anywhere else in low orbit. It is not dangerous to people on the ground, but it is strange enough that engineers plan around it, and researchers still argue about what it means. Picture the magnetic field as a kind of skin over the whole Earth, thick in most places, thin in others. Over the South Atlantic, that skin has been getting thinner for at least 200 years, maybe longer. Ground stations and old ship logs from the 1800s hint that sailors crossing this stretch of ocean noticed odd compass readings even then. The patch has not stayed still either. It has drifted slowly westward over recent decades, and in the last few years it seems to have split into two separate lobes, like a single shadow dividing into twins. No one fully agrees on what causes it. One idea points far below our feet, to the boundary between the core and the mantle, that rocky layer above the molten iron. Near the base of the mantle, beneath Africa, sits a strange structure, a region where seismic waves slow down as they pass through, suggesting something dense and unusual sits there. Some researchers think this structure disturbs the flow of molten iron in the outer core just beneath it, weakening the magnetic field that rises up through the rock above. It is a compelling picture, but it remains a hypothesis built from indirect clues, not something anyone has seen directly. A different idea treats the anomaly as simply one ripple among many in a fluid system that is always rippling. The outer core churns constantly, its iron currents shifting in patterns too complex to fully model. In this view, weak patches come and go across the globe over centuries, and the South Atlantic anomaly is not necessarily special. It might be a phase, one that could fade in a few hundred years, the way similar weak patches may have appeared and dissolved in the deep past. The trouble is that we have only been measuring the field precisely for about 2 centuries, a blink of an eye next to the tens of thousands of years a full reversal seems to take. This is where the anomaly connects to the larger mystery of reversals. Some scientists wonder if this weak spot is an early sign, a preview of the kind of scattered, patchy field that tends to appear right before the poles fully trade places. Others push back firmly, noting that similar anomalies have shown up in the paleomagnetic record, that written history preserved in old rock, without leading to any reversal at all. A weakening in one region, they argue, is not the same as a global collapse of the field. The two processes might be related, or they might simply look similar from a distance while having nothing to do with each other. What makes the anomaly feel so counterintuitive is the shape of it. Most people imagine a magnetic field weakening evenly, like a light bulb, slowly dimming across a whole room. Instead, the real field is lumpy and uneven, strong in some places, thin in others, shifting unevenly across the decades. The South Atlantic anomaly shows that a global reversal, if one is coming, might not announce itself with a single dramatic signal. It might arrive first as a patchwork of quiet, local surprises, each one easy to dismiss on its own. Satellites, like the European Space Agency's Swarm mission, now track these changes in fine detail, mapping the field's strength almost year by year. The data shows the anomaly growing, splitting, drifting, behaving in ways that resist any simple story. Some researchers see this as evidence of an unstable outer core nearing some kind of threshold. Others see ordinary turbulence, the natural noise of a molten iron ocean that has churned this way for billions of years without any grand event on the horizon. For now, the honest answer is that no one knows for certain what the South Atlantic anomaly means. It might be a footprint of deep mantle rock disturbing the currents below. It might be a passing eddy in a fluid system too vast and too dynamic to predict. It sits there quietly above the ocean, a soft depression in an invisible field, inviting anyone paying attention to wonder what it is trying to tell us, if anything at all. Let's picture the field as it stands today, right now, while you rest under it without feeling a thing. Earth's magnetic field is not fixed. It has been losing strength, slowly, for at least the last 200 years. Measurements taken by satellites and ground stations show the overall field has weakened by about 9% since the 1800s. That sounds like a lot, but the field is still strong enough to protect us, still strong enough to turn the compass needle north, still strong enough to paint the sky green and pink at the poles when solar particles come streaming in. Some researchers wonder if this weakening is the opening chapter of a full reversal, the kind of event that has happened many times across deep time. Others believe it may simply be a normal wobble, the kind of change the field goes through, often without ever tipping over into something new. Both ideas fit the evidence we have so far. That is the heart of the open question tonight. We do not know which chapter of the story we are actually in. The South Atlantic anomaly gives us one thread to follow. That patch of weaker field, stretching from South America to Southern Africa, has been growing wider and drifting westward for decades. Some scientists see this as a small preview, a local rehearsal for what a global reversal might look like on a much larger stage. Other scientists caution that the anomaly may simply be a normal feature of a churning outer core, unrelated to any coming flip. The same swirling ion currents that build the field also build its dents and weak spots, and not every dent leads somewhere large. Think of the whole system as a kind of quiet orchestra, playing far beneath your feet. The outer core, that layer of liquid iron and nickel, roughly 2,000 kilometers thick, moves in slow, restless currents, driven by heat rising from the inner core. This movement creates electric currents, and those currents create the magnetic field that reaches far out into space. The field, in turn, shields the atmosphere from the constant push of the solar wind, that stream of charged particles flowing outward from the sun. Every part depends on every other part, and none of them move at the same pace as the world above. The sun plays its own part in this quiet symphony. Solar wind presses against the magnetic field every second of every day, shaping it into a long teardrop, compressed on the side facing the sun and stretched into a tail on the side facing away. Day, weaker magnetic field would let more of that solar wind through, and more charged particles would reach the upper atmosphere. Some researchers think this could increase radiation levels at the surface during a reversal, though how much of an increase remains genuinely unclear. Others point out that the atmosphere itself provides real protection, even without a strong magnetic field, and that early Earth had life before the modern field even existed in its current form. None of these systems act alone. The core's heat drives the field. The field guides the solar wind around the planet instead of through it. The atmosphere absorbs what does get past the field, and the ocean and land beneath it all keep moving through their own slow rhythms, mostly unaware of the invisible drama above and below them. It is a chain of dependence, each link shaped by the ones beside it, stretching from the deep iron heart of the planet to the empty space beyond the sky. And still, no one can say with confidence whether this current weakening is the start of something larger. The paleomagnetic record, that story written into old rocks and seafloor sediment, shows reversals happening at uneven intervals, sometimes tens of thousands of years apart, sometimes hundreds of thousands. There is no steady clock ticking toward the next one. There is only a pattern of past events, read backward through stone and lava, offering hints rather than certainty. This slow decline we see today could be an early tremor before a great change, or it could be one of many ordinary fluctuations the field has shown before, then quietly recovered from. Lying here now, wrapped in the ordinary dark of your own room, you are resting beneath a system still writing its own next chapter. Iron currents move without pause far below the ground. The sun pushes without pause far above the sky, and between those two forces, the field bends and stretches, weakens and steadies, in a rhythm no one has fully learned to read. Whether tonight is part of a slow beginning or simply another quiet pause, no one yet knows. The orchestra plays on, unseen, and we listen from a great distance, still learning the song. Let's imagine a world many thousands of years ago, one that went through a reversal, or perhaps came close to one. What did that world feel like to the creatures living in it? This is one of the quiet, patient questions that geologists carry with them. The rocks can tell us when the field flipped or wavered. They cannot tell us if anything alive noticed at all. Picture a forest in that ancient time, thick with ferns and heavy-limbed trees, rain falling softly through a green and endless canopy. Somewhere above that canopy, the magnetic field that wraps our planet was thinning, growing weaker than it is today. We know this from the magnetized minerals locked inside lava flows and ocean sediments, tiny compass needles frozen in stone. What we do not know, not with certainty, is whether the animals below ever felt a difference. Some researchers wonder if a weaker field let in more cosmic rays, those high-energy particles that arrive from beyond our planet. The magnetic field acts like a loose net, deflecting many of these particles before they reach the ground. If the net grew thin during a reversal, slightly more radiation may have reached the surface. One idea suggests this could have nudged rates of mutation in some living things ever so slightly over long stretches of time. This remains speculative, a hypothesis rather than a settled finding, and many scientists think the effect, if it exists at all, would have been small. Others look at the fossil record for signs of change during past reversals and find very little that stands out clearly. Extinctions do appear in Earth's deep past, but when researchers line up the timing of magnetic reversals with the timing of extinction events, the match is weak at best. Most reversals in the geologic record show no clear link to mass die-offs. This is one of the steadier findings in the field, even if it disappoints anyone hoping for a dramatic cause and effect story. Still, the question has not been closed entirely. A small number of studies have pointed to unusual layers in the fossil record that sit close in time to certain reversals, layers with shifts in the abundance of particular marine organisms. Whether these shifts came from the magnetic change itself, from unrelated shifts in climate or sea level, or from simple coincidence, remains an open question. Correlation in deep time is a slippery thing to prove. Millions of years compress into thin bands of rock, and events that felt separated by centuries can appear to line up in the same layer. Consider, too, the pace of these events. A reversal does not happen in a day or a season. The transition, based on the geologic evidence, seems to unfold over hundreds to a few thousand years, with the field weakening, wandering, and finally settling into its new direction. A creature living through this would not experience a sudden flip like a switch turning off. It would experience a field that behaves strangely for a long stretch of its own lifetime and the lifetimes of its children, without any single dramatic moment to mark the change. This slow pace changes how we think about danger. A weakened field lasting centuries is not the same as a field vanishing overnight. Life on Earth has already lived through many reversals across hundreds of millions of years. Quietly, without leaving behind clear signs of crisis, the mammals that eventually gave rise to us were here for at least a few of these events. Whatever happened to the field around them, they carried on, adapted, and kept living in their soft-lit forests and open grasslands. Some scientists find comfort in this pattern. They see it as evidence that reversals are, in the language of deep time, a rather ordinary event, one the planet and its living things have absorbed again and again. Others caution that ordinary in the past does not guarantee ordinary now, since today's world holds delicate technology and dense human populations that ancient ecosystems never had to account for. The past speaks quietly and only in fragments, leaving room for both comfort and caution. For now, the honest answer is a patient one. The record shows reversals happening without clear catastrophe, and it also shows us how much of that ancient world is simply lost to time. We do not know exactly how life felt the change, only that life continued. Somewhere in old stone, tiny grains of magnetite still hold the memory of a world where north and south traded places. Slowly, wild ferns kept growing and rivers kept running, indifferent to the invisible compass turning above them. Picture a small bird resting for a moment on a fence post in autumn. Soon it will lift into the night sky and fly a path it has never flown before, thousands of miles, to a place it has never seen. It will not get lost. Somewhere in its small body, it seems to sense the invisible lines of Earth's magnetic field, the same field born in the churning iron far below our feet. How it does this remains one of the gentler mysteries tied to our shifting compass. Scientists call this ability magnetoreception, the sensing of magnetic fields, and it shows up across a surprising range of animals. Some birds appear to carry tiny traces of iron in their beaks or inner ears, and one idea is that these specks act like microscopic needles, tugged ever so slightly by the planet's field. Another theory points to something stranger, hidden in the eye itself. Certain proteins called cryptochromes may respond to Earth's magnetism through a delicate quantum effect, one that some researchers think lets birds actually see the field as a faint pattern of light and shadow layered over the world around them. Sea turtles seem to carry their own magnetic memory. A hatchling turtle, barely larger than a coin, crawls into the ocean off the coast where it was born and swims out into open water. Years later, as an adult, it may return to that same stretch of coastline to lay its own eggs. Researchers who study this have found that turtles appear to imprint on the magnetic signature of their birth beach, a kind of address written in invisible lines rather than ink. The idea remains supported by strong evidence, though scientists are still working out the fine details of how the memory is stored and recalled. Whales, too, may read this same hidden map as they cross entire oceans. Some researchers have looked at strandings, the sad and still puzzling cases when whales find themselves beached on shorelines far from open water, and wondered whether disruptions in the magnetic field might play a role. A patch of unusually weak or twisted magnetism along a whale's path could, in theory, confuse an animal that navigates partly by feeling that field. This idea remains debated, and many other factors, from underwater terrain to storms to illness, are also part of the conversation. No single cause has been confirmed. All of this raises a quiet question that sits at the center of tonight's episode. If so much of life depends on a stable, readable magnetic field, what happens to that invisible map during a reversal, the slow and dramatic event when north and south trade places over the span of centuries or thousands of years? During a full reversal, the field does not vanish, but it can weaken and grow far more complicated, breaking into multiple weaker patches instead of one clean set of poles. For a bird crossing a continent by magnetic field, that could mean the familiar lines it has always followed grow faint, or strange, or momentarily unreadable. We do not know for certain what this would look like from the inside of a bird's mind, or whether animals would simply adjust, using stars, or scent, or the coastline itself as backup guides. Many species that rely on magnetic sensing also use other cues, and this layering may offer a kind of quiet insurance. Still, the paleomagnetic record, the magnetic history written into ancient rock, does not tell us directly whether past reversals caused confusion among migrating animals. That story if it happened at all, left no fossils, no fixed evidence we can point to today. There is a soft kind of wonder in imagining it anyway. Picture a formation of geese passing over a weakening field tens of thousands of years ago. Their inner compass points drifting and doubling, the sky above them the same, the ground below them unchanged. At the invisible layer connecting the two grown suddenly uncertain. Did they simply find another way home? Did the map matter less than we think, or did some creatures adjust so slowly across generations that the shift barely registered at all? For now, the light we can measure moves through auroras and solar particles, through the shimmer above the poles that marks where the field bends and gathers. But the deeper light, the one guiding a bird or a whale or a small green turtle across a trackless ocean, remains only partly understood. It flickers somewhere between biology and physics, between what we can prove and what we can only carefully suggest. And so the question stays open, resting quietly beside all the others, waiting for a future scientist, or perhaps a future night like this one, to bring it a little further into view. Close your eyes for a moment and picture a satellite, quiet and small, moving through the dark above the clouds. It hums with electricity. Its instruments listen to the space around it, and somewhere inside, tiny sensors respond to the pull of Earth's magnetic field. That pull is soft, almost too soft to imagine, and yet without it, many of our machines would lose their way. We do not usually think of magnetism as something with a sound, but scientists have learned to take the invisible hum of the magnetic field and turn it into tones we can hear, low pulses that rise and fall as the field bends and drifts. When researchers play back years of magnetic data as sound, it feels a little like breathing, slow, steady, alive. And somewhere within that breathing is a quiet, unanswered question. What happens to all our machines if that breath changes? A compass needle finds north because it feels the shape of the magnetic field, that great invisible shell that wraps around our planet like a soft glove. Ships have trusted it for centuries. Airplanes still use it today. If the poles were ever to reverse, or even wander through a long, unstable stretch on the way to a reversal, compasses would drift and settle in new and unfamiliar places. This would not happen suddenly. Most researchers believe it would unfold across centuries, maybe longer, giving instruments and industries time to adjust their charts and calibrations. Satellites face a more delicate concern. Their orbits pass through invisible rivers of charged particles that stream from the sun, called the solar wind. Right now, the magnetic field acts like a wide, curved shield, gently deflecting most of that wind around the planet. If the field grew weaker during a reversal, some researchers wonder whether satellites might absorb more of that charged particle exposure, slowly wearing down their circuits faster than usual. Others note that satellites already survive short bursts of heavy solar activity and might simply need extra shielding. Not a complete redesign, nobody knows for certain, because we have never watched a full reversal with modern instruments running. There is also the electrical grid to think about, the vast web of wires that carries power into our homes. Strong solar storms can already induce extra electrical current in long transmission lines, sometimes enough to strain transformers. A weaker global field might make the planet slightly more sensitive to these solar disturbances, though the size of that effect remains an open question. Some scientists suspect the change would be gradual and small. Others think even minor shifts, layered on top of the sun's ordinary unpredictable moods, could occasionally cause bigger headaches for power engineers than they see today. Then there is GPS, that quiet system so many of us rely on without ever noticing it. Its accuracy depends partly on knowing the exact shape of the magnetic field, since the field influences the upper atmosphere layers that satellite signals must pass through. If the field structure changed in unusual ways, positioning systems might need more frequent updates and corrections. Engineers already adjust their models regularly for the field's slow, ordinary drift. A larger shift would simply mean more frequent tuning, though how disruptive that tuning might feel to daily life is still unclear. It's worth remembering that Earth has flipped its magnetic poles many times across deep time. Long before satellites, long before power grids, long before compasses ever existed, life continued. Migrating birds found their way. Ancient forests grew. This offers a kind of quiet reassurance, though it does not fully answer today's question, because our machines are new. They have never faced a full reversal, and their delicate circuits behave differently than a bird's inner sense of direction, or the slow patience of a growing tree. Some researchers imagine a future where engineers build in more resilience ahead of time, adding shielding to satellites, hardening transformers, refining backup systems for navigation. Others believe we are getting ahead of ourselves, since a true reversal might still be thousands of years away, or might begin as a partial excursion that never fully completes. The honest answer is that we simply do not know how disruptive it would be, or how much warning we might have before real changes begin. For now, the magnetic field keeps its low, steady hum, the sound of something ancient and mostly unseen, still holding its shape around us. Whether that hum will ever waver into something stranger remains. One of the open questions the Earth keeps to itself, humming on, unhurried, into the quiet dark of the night sky above us. Let's picture the sun for a moment, not as a warm light in the sky, but as something wilder. The sun sends out a constant stream of charged particles, a kind of wind made of matter instead of air. Scientists call it the solar wind, and it rushes outward in every direction. At speeds that can top 1,000,000 miles an hour, it carries pieces of the sun itself, tiny charged fragments, across the empty space between us and that distant fire. Earth sits in the path of this wind, and without protection, it would simply strip away pieces of our atmosphere over time. This is where the magnetic field earns its quiet importance. That invisible shape, generated far below our feet in the swirling iron of the outer core, reaches out into space and forms a kind of shell around the planet. Scientists call this shell the magnetosphere, and it deflects most of the solar wind before it ever touches the air we breathe. The shape of this shield is not simple or round. On the side facing the sun, the solar wind presses the field inward, compressing it into a rounded front edge. On the night side, away from the sun, the field stretches out into a long tail, sometimes reaching millions of miles into space. Shaped like a comet made of invisible force, inside this tail, particles get trapped and channeled, some of them eventually spiraling down toward the poles, where they collide with gases in the upper air and glow. This is one explanation for the aurora, those slow curtains of green and red light that drift over the far north and far south. The math behind this system has its own kind of elegance. The strength of the field falls off with distance in a fairly predictable way, following patterns that physicists can model with real precision, at least when the field is behaving normally. Close to Earth, the field is strong enough to hold back nearly all of the solar wind. Farther out, at the boundary of the magnetosphere, the pressure from the sun and the pressure from Earth's field settle into a kind of balance point, a place where the two forces meet and neither one wins. That balance point shifts a little with the strength of solar activity, breathing in and out over months and years. Here is where the mystery deepens. If the magnetic field weakens dramatically during a reversal, as the paleomagnetic record suggests it does, that balance point would move. The shield would sit closer to the ground, and the shape of the shell would likely change in ways researchers are still working out. Some models suggest the field could drop to a small fraction of its usual strength for centuries at a time, before settling back into a clear pattern with reversed polarity. Other models suggest the field never fully disappears, even at its weakest, because complex, uneven patches of magnetism might continue to form in scattered regions across the globe. Even without one strong, unified shape, this uneven weakening connects to something researchers already watch today. In the South Atlantic Anomaly, a patch of unusually low field strength, stretching across parts of South America and the ocean nearby. Satellites in that region receive higher doses of radiation, since the shielding above it is thinner than average. Some scientists wonder whether this patch is an early sign of a coming reversal. Others point out that similar weak patches have come and gone before without leading to a full flip. So the presence of one weak spot does not settle the question either way. What remains genuinely open is how much thinner the shield would need to become before it lets through meaningfully more of the solar wind, and what that would mean for life at the surface. The atmosphere itself offers a second layer of protection, absorbing much of the radiation that does get past a weakened field. Researchers studying past reversals have looked for signs of increased radiation in old ice cores and ancient sediments, and so far the evidence has not pointed to any clear crisis. Still, the reversals in the deep past happened before humans built satellites, power grids, or global networks of communication, so it is hard to say with certainty what a modern transition would look like. The numbers describing the solar wind and the shape of our shield are precise and well understood, at least for the field as it exists now. What those same equations would predict during a reversal, when the source of the field itself is in flux, is still an open question researchers continue to explore with patient curiosity, one careful model at a time. Picture a scientist sitting before a bank of quiet screens, watching numbers drift across a model of the Earth's core. The model is beautiful. It is also, in its own way, a guest dressed up in mathematics. This is where we find ourselves tonight, in the space between what we can calculate and what we can actually know about the next great turning of the compass. Building a model of the outer core. That shell of liquid iron and nickel roughly 3,000 kilometers below your feet takes some courage. The core is too hot, too deep, and too far away to touch directly. No probe has ever been sent there, and none ever will be. Everything scientists know about its motion comes from indirect clues: the pull of gravity, the whisper of seismic waves passing through, and the faint signature the field leaves behind on the surface above. From these clues, researchers build equations that try to capture how molten metal churns and twists in the dark. These equations are called dynamo models, named for the dynamo effect that keeps the field alive in the first place. Feed a supercomputer enough starting conditions, enough estimates of heat and pressure and rotation, and it will produce a magnetic field that behaves something like our own. Some models even produce their own spontaneous reversals, flipping north to south without anyone telling them to. This is a small triumph. It suggests the basic physics is understood, at least in outline. But it does not tell us when the real Earth will do the same thing, because the model's inner world is not the real inner world. It is a simplified cousin, useful for testing ideas, unreliable for making calendars. Here is where the fragility of the whole system becomes clear. Small changes in the assumptions fed into a model, how fast the core spins, how heat escapes toward the mantle, how turbulent the flow becomes, can produce wildly different outcomes. One version of the model might show a stable field for 1,000,000 years. Another, built on numbers only slightly different, might show 3 reversals in that same stretch of time. The system, it seems, sits close to some kind of edge. It does not take much to tip it one way or another, and scientists still argue about which factors matter most. Some researchers lean toward heat flow at the boundary between the core and the mantle as the deciding variable, the slow leaking of warmth outward that stirs the molten iron beneath. Others point to the rotation of the Earth itself, and how tiny wobbles in that spin might nudge the currents below into new patterns. Still others wonder if the field's instability is simply a natural feature of any dynamo this size, something built into the system from the very beginning, requiring no outside trigger at all. None of these ideas has been ruled out. None has been confirmed beyond doubt. What this means, practically, is that no one can offer a date for the next reversal. Not next year, not next century, not within 1,000 years, with any real confidence. The field has weakened by about 9% over the last 2 centuries, and that number invites speculation. But weakening has happened before, without leading to a full reversal, and the current pace could slow, reverse itself, or hold steady for reasons not yet understood. A prediction built on this kind of thin evidence would be little more than a story dressed as science. There is something almost calming in admitting this limit. The Earth's magnetic field is not a machine running on a schedule we simply have not decoded. It is closer to weather in that sense, shaped by so many overlapping forces that precise forecasting, months or years ahead, remains out of reach even with modern instruments. Meteorologists can tell you the general shape of a season. They cannot tell you the exact date of a storm 10 years out. The core's slow churning may work the same way, offering patterns without appointments. For now, satellites like those in the European Space Agency's Swarm mission keep watching from orbit, tracking the field's shape month by month, mapping its slow drift and its curious weak patches. Their data feeds back into the models, refining the guesses, sharpening the questions, even when it cannot yet answer them. It is patient work, done in small increments, a kind of steady watching that rarely makes headlines, but slowly deepens understanding. So the field remains what it has always been to us, a delicate, moving thing, sustained by forces we can describe but not fully predict, drifting under a sky it has protected for longer than there have been eyes to notice it. There is another kind of event, quieter than a full reversal, and it may be even harder to explain. Scientists call it an excursion. Picture the compass needle wandering far from true north, tilting, wobbling, sometimes swinging halfway toward the south. Then, instead of finishing the turn, it slowly wanders back home. The field never fully flips, it just loses its balance for a while, like a spinning top that leans hard to one side before it rights itself again. The most studied example is called the La Champ excursion. It happened about 41,000 years ago, named for a village in France where volcanic rock first captured the record. During this event, researchers believe the magnetic field weakened dramatically, perhaps dropping to a small fraction of its usual strength. The magnetic poles appear to have wandered a great distance from their normal positions, maybe even approaching the opposite hemisphere, before slowly drifting back. The whole episode seems to have lasted only a few hundred years, which is remarkably brief in geological time. What makes excursions so puzzling is the question of why they stop. A true reversal completes its journey. The old north becomes the new south, and the field settles into that new arrangement for a long stretch of time. often hundreds of thousands of years. An excursion begins the same way, with the same weakening and wandering. But then it seems to change its mind. Some researchers wonder if excursions are simply failed reversals, attempts that ran out of energy before they could finish. Others propose that excursions and reversals are actually different processes entirely, driven by separate patterns of motion deep in the outer core, that liquid iron layer whose churning currents generate the field in the first place. The evidence for what happened during last jump comes from an unusual combination of sources. Volcanic rock in France holds a magnetic signature frozen in place when the lava cooled. Ice cores from Greenland and Antarctica, layered like the pages of a very slow book, show spikes in a rare form of the element beryllium, a marker that forms when cosmic rays strike the atmosphere more freely. A weaker magnetic field lets in more of these high-energy particles from space, and the ice remembers that increase even though nothing about it is visible to the eye. Sediment cores from the ocean floor around the world show a similar pattern at the same layer, which gives scientists confidence that Lachamp was a real global event and not just a local anomaly in one patch of rock. Yet many questions remain wide open. Scientists still do not fully understand what determines whether a weakening field will complete a reversal or pull back into an excursion. There is no confirmed count of how many excursions have happened throughout Earth's long history, since fainter or shorter events may leave a much weaker signature in the rock, one that is easy to miss or hard to date precisely. Some researchers suspect there could be many more excursions hiding in the geological record than we currently recognize, simply because they are more subtle and more easily erased by time. There is also the deeper question of what causes the outer core's flow to become unstable in the first place. The core's convection, that great slow churning of liquid iron, driven by heat from the inner core, is a chaotic system. Small differences in temperature or composition deep inside the Earth could, in theory, be enough to nudge the field toward an excursion rather than a full reversal, or toward no disruption at all. Modeling this kind of turbulence with any precision remains one of the harder problems in geophysics, partly because no one can measure the outer core directly. Everything scientists infer about it comes from indirect clues, like the magnetic signature and small wobbles in Earth's rotation. For someone lying in the dark tonight, there is something quietly comforting in this uncertainty. The Earth's magnetic field has wandered before, weakened before, tilted far off its usual course, and then found its way back without ever completing the full turn. Whether the field is now easing toward another excursion, or possibly the beginning of a true reversal, is a question that remains unanswered. The rock and ice hold pieces of the story, but not the whole of it. Perhaps that is fitting for a planet whose deepest layers we can still only imagine, sensed indirectly, one faint magnetic whisper at a time. Let your mind drift for a moment past our own planet and out toward its neighbors. Earth is not the only world with a story written in iron and motion. Mars, small and red and quiet now, once had a magnetic field of its own. We know this because ancient Martian rocks scattered across its dusty surface still hold traces of magnetism frozen inside them, laid down billions of years ago. Something, long ago, was stirring beneath that surface, much like the churn inside our own planet's core. Then, sometime in Mars's deep past, that field faded. Nobody knows for certain why. One idea is that Mars, being smaller than Earth, cooled too quickly. Its core, once molten and moving, may have hardened into stillness, the way a pot of soup thickens as it cools on a stove. Without a moving core, There is no dynamo, no engine to generate a field. Another idea points to something more violent, a giant impact that disrupted the flow of heat inside the planet and shut the whole system down. Both remain theories. Mars keeps its answer buried, somewhere under all that red dust. What happened next on Mars may be a quiet warning, or it may simply be a different story entirely, without a magnetic field. Mars lost much of its atmosphere over time, worn away by the constant push of the solar wind, that steady stream of charged particles flowing outward from the sun. Earth's field, weak as it sometimes gets, still holds that wind at bay. Whether a full reversal here would ever bring us close to Mars's fate is not something anyone can say with confidence. Our atmosphere is thicker, our planet larger, and the timescales involved are almost impossible to picture. Still, looking at that dry, reddish world gives us a strange kind of company in the dark, a reminder that magnetic fields are not permanent gifts. Mercury offers a different puzzle. It is a small, rocky world sitting close to the sun, and by many predictions, it should have gone cold and still long ago, just like Mars. Yet Mercury has a magnetic field, faint but real, discovered by spacecraft that passed close enough to feel it. Nobody expected this. One theory suggests Mercury's core has not fully solidified, that a thin shell of liquid iron still moves within it, driven by heat, escaping slowly into space. Another theory wonders if the field is a kind of leftover, a fossil signature locked into ancient rock, rather than something being generated fresh. Right now, the debate continues, unresolved, much like our own questions about the inner workings of Earth's core. Then there is Jupiter, vast and gaseous, wrapped in a magnetic field so enormous it would stretch if you could see it with your own eyes, several times wider across the sky than our moon appears from Earth. Jupiter's field comes not from iron, but from a strange layer of hydrogen squeezed under such tremendous pressure that it behaves like a metal, conducting electricity and churning in slow, powerful currents. It is a completely different recipe from our own planet's core, yet it produces the same basic result, a field that reaches out into space and shapes the world around it. Each of these worlds, so different from one another, points to the same quiet truth. A magnetic field is not a fixed feature of a planet. It is a process, an ongoing event, dependent on heat and motion and the particular architecture hidden inside each world. It can fade, as it seems to have done on Mars. It can persist in surprising, faint forms, as it does on Mercury. It can grow into something almost incomprehensible in scale, as it does around Jupiter. Earth's field, with its slow, wandering poles and its rare, dramatic reversals, is simply one version of this larger planetary story, unfolding on its own timeline. Looking outward like this does not answer the question of what triggers a reversal here, or when the next one might begin. It does something gentler than that. It places our restless compass in the context of a wider group of restless worlds, each one working out its own relationship with heat, motion, and time. Some fields fade forever, some flip again and again. Some may simply be settling into a new and quieter existence we do not yet understand. Whatever Earth's core is doing right now, in the dark, under thousands of miles of rock, it is doing what planetary cores seem to do everywhere, changing, slowly, according to rules we are still learning to read. Right now, in quiet rooms full of humming instruments, people are still watching the compass needle of the whole planet. Satellites circle high above us, tracing the faint pull of the magnetic field as it drifts and dips. Ground stations sit in lonely places, from the Arctic tundra to the volcanic islands of the South Atlantic, each one recording tiny changes that might mean nothing or might mean everything. Nobody is waiting for a sudden alarm. They are watching for a pattern, the way you might watch clouds for a change in the weather. Patient and unhurried, one thing they track closely is the strength of the field itself. It has weakened by a small amount over the last 2 centuries, and that number gets checked and rechecked every year. A few researchers see this as a hint of a coming reversal, a slow inhale before an ancient exhale. Other researchers point out that similar dips have happened before without leading anywhere near a full flip. The truth is that a weakening field could be an early sign, or it could be an ordinary flicker in a system that has always flickered. Both readings fit the same data. They also watch the South Atlantic anomaly, that strange patch of weaker field stretching from South America to Southern Africa. Some models suggest it is growing wider. Other models suggest it is simply drifting, the way a puddle might shift shape on tilted ground without actually spreading. Scientists still argue about whether this patch is a small step toward reversal, or just a quiet feature of the deep, churning outer core, that layer of liquid iron and nickel far beneath our feet. Nobody can say for certain, and that uncertainty is treated seriously here, not brushed aside. Deep underground, other tools help fill in the picture. Seismic waves, the gentle shudders sent out by earthquakes, pass through the core and come back changed by what they moved through. By studying those changes, scientists build rough pictures of the swirling currents inside the outer core, the same currents that seem to generate the magnetic field in the first place. It is a bit like trying to understand a storm by only feeling the wind on your face. The picture is useful, but it stays incomplete. Supercomputers now run models of the core's motion, testing different conditions to see which ones might trigger a reversal. Some models produce flips every few 100,000 years, which roughly matches what old rocks tell us. Other models run for a very long simulated time and never flip at all. Small changes in temperature or flow inside the model can shift the outcome completely. This tells scientists something important. The core's behavior may be so sensitive that no one, not even with the best equipment we have, can predict the timing of the next reversal with real confidence. Some researchers hope future instruments, perhaps buried deep boreholes or improved satellite networks, might catch a clearer warning sign. Others suspect that even with perfect measurements, this system may stay unpredictable at its core, the way weather stays partly unpredictable even with excellent forecasting tools. Both views sit together in the same scientific conversation, neither one fully winning out. It's worth remembering how small our slice of observation really is. We have only had magnetic instruments capable of detailed measurement for a couple of 100 years, a blink of time next to the hundreds of thousands of years between reversals. Imagine trying to understand the pattern of ocean tides from watching just one wave. That is roughly the scale of what we are working with here, and it is part of why the mystery stays so open, and there is something quietly moving in this kind of patience. Nobody rushes toward an answer. Instead, generations of researchers pass along their instruments and their questions, adding a little more data year after year, the way old stargazers once passed along their star charts to the ones who came after. The iron in the planet's core, they say, formed from the same collapsing cloud of gas and dust that made the sun and the stars around us. In a very real sense, the restless heart of the earth carries material born in the same great cosmic fire that made our bones and our blood. We are made from the same beginnings as the planet we study. So, the watching continues, calm and steady, without urgency. The compass needle rests in its little glass case, pointing toward a north that has moved before and may move again. For now, it simply waits, along with the rest of us, for an answer written in the slow language of deep time. Somewhere below your feet, right now, a sea of molten iron is turning. It has no calendar and no clock. It moves the way it has always moved, slow and dark and patient, thousands of miles beneath the quiet room where you are lying. It does not know that we call it a core. It does not know that we have named its wanderings, mapped its stripes in old lava, or given the year 41,000 years ago a name of its own. It simply moves, and somewhere in that movement, hidden from every instrument we have ever built, is the answer to when north will become south again. We do not know that answer tonight. We may not know it for a long while yet. Perhaps someone alive today will feel a compass needle drift, decade by decade, until it no longer points where it once did. Perhaps that shift will not come for 1,000 years or 10,000, long after every person now listening has become part of the soil beneath some future forest. The field may be weakening because it is beginning a great turn, or it may simply be doing what it has always done, breathing in slow, uneven cycles that never quite become a full reversal at all. Both ideas remain open. Both are held gently by scientists who keep watching, keep measuring, and keep admitting how much is still unknown. There is something soothing in that not knowing if you let it settle. The Earth has flipped its poles hundreds of times across its long life, and life did not end. Forests kept growing. Oceans kept their tides. Whales and birds, guided by senses we barely understand, found their way home again and again, even through ages when the compass in the sky above them must have wavered and dimmed. The planet has always been a place of slow change, happening underneath sturdy, ordinary days. Tonight is one of those ordinary days. The core turns, the field bends, and you are still here, safe under a roof, under a sky, under a magnetic shield that has protected this world for billions of years and shows no sign of vanishing before morning. Picture it, if you like, one more time. As your eyes grow heavy, picture the Earth from far above, a soft blue curve turning slowly in the dark. Around it, invisible, a great looping shield of magnetism bends outward into space, catching the solar wind the way a wide hand cups a small flame. Underneath the oceans, unseen stripes of ancient rock lie frozen in the sea floor, quietly recording a story written over millions of years. Somewhere in the South Atlantic, the field dips low, a small imperfection in an otherwise steady breath. None of it demands anything from you. It simply exists, layer upon layer, deep time resting beneath deep time. You do not need to solve this mystery to rest well tonight. You do not need to know if the next reversal begins in your lifetime or in some age long after, among people who will look back at us the way we look back at the ancient volcanoes that first recorded this whole quiet story. It is enough to know the story is still being written patiently by a planet that has never been in a hurry. The iron keeps churning, the field keeps holding. The stars outside your window keep their same old places, at least for tonight, and the ocean somewhere far away keeps rising and falling, under a calm and steady moon. Let that be the last picture you carry with you, not a spinning compass needle, uncertain and searching, but a wide, dark ocean under soft light, moving the way it has always moved, unhurried and sure of itself. Let the low hum of the Earth's hidden furnace become something like a lullaby, a heartbeat too deep and too slow for us to ever truly hear, felt only in the quiet certainty that morning will come again. The mystery will still be there tomorrow, waiting patiently, the same way it has waited for millions of years already. Tonight, you do not have to hold it. Tonight, you only have to rest, held by a world far older and far steadier than any worry that follows you into sleep. Subscribe for a brand new Earth topic every night. One tap, and something wonderful is waiting for you tomorrow. Sweet dreams.